Welcome to aminacademy.com. In physics regarding capacitance, let us do some solving problem. Look at these examples. A capacitor has capacitance 10 microfarad with air between its plates. Determine its capacitance when a dielectric with dielectric constant 6 is placed between its plates. Here, already capacitance is 10 microfarad. Between them is air. Now, having dielectric constant 6 is placed between its plates, then capacitance C equal K times that 10 microfarad, 10 into minus 6, then K is 6 into 10 into 10 power minus 6 equal 60 into 10 power minus 6, then which is equal 60 microfarad, because in dielectric increase, the constant of the dielectric increase, that capacitance also increase. Then next question, what is the charge on 500 picofarad capacitance when it is charged to a voltage 1.5 kilovolts? Now charge Q equal CV. Therefore Q equal capacitance is 500 into 10 power minus 12. Picofarad is 10 power minus 2 farad into 1.5 kilowatt, 1500 volt. So which is equal 15 into 5 is 75. 4 zeros into 10 power minus 12. That is here coulomb. So which is equal then microcoulomb, we can write this much coulomb. That 0.75 into 0.75 microcoulomb. That means here, if you multiply 10 power 6, this becomes microcoulomb, then 10 power 6 minus 6, then after moving the point, it becomes 0.75 microcoulomb. Next question, 1.5 microfarad capacitor is charged to 4 kilovolt. Compute the energy stored. Energy stored equals to half QE, half into Q, Q means half CV, half QE equal to half CV square. Capacitance charge becomes capacitance. Now half CV square, that is half into C is 1.5 into 10 to the power of minus 6 the square. No, well, now here into V is 4000 square, which is equal 1.5 into 4000 into 4000 into 4000 divided by 2, which is equal 12 joules. Then that is energy stored is 12 joules. That means 1.5 microfarad capacitor is charged with 4 kilovolt, means this is fully charged. Energy required is 12 joules stored. Next one, two capacitors are connected in series and parallel across the voltage 1.2 kilovolt as shown in the figure. Calculate the equivalent capacitance in terminal, the magnitude of the charge on each capacitor, the potential difference on each capacitor, and energy stored in the capacitors. We'll do this problem in two ways. First, series. Here in series circuit, in series, look at here, 1 by capacitor equivalent equal to 1 by C1 plus 1 by C2. This is a combination for series combination, that is equal 1 over 3 plus 1 over 6, which is equal 6 is an LCM, 2 plus 1 plus 2, 1 plus 2, 3 by 6, that is half. 1 by C equivalent equal to 1 by 2, therefore then C equivalent is 2 reciprocal, 2 microfarad. Then same for series, equivalent C equivalent equal to C1 plus C2, which is equal 6 plus 2 plus 6, 8 microfarad. That means here in series circuit, capacitance is added. Now here in parallel circuit, the charge in each capacitor is same. Therefore, Q1 equal Q2 equal to general Q, which is equal C equivalent into voltage. C equivalent is 2 microfarad, that is minus 12 farad, into 1 kilowatt means 1000 volt, which is equal to becomes microfarad. 2 potent 2 into 2 nano, here 2 nanocoulombs is equal to into 10 power 9 coulomb, which is equal to nanocoulomb. That means charge on each capacitor is 2 nanocoulomb. Here Q1, here for parallel circuit charges are different. So Q1 equal to C1 V1. C1 V1 here in parallel circuit voltages are same, therefore C1 V1, which is equal, C is C1 is 2 into 120 volts, which is equal 2 into 10 power minus 6 into 120 is equal 240 into 10 power minus 6 here, which is equal 0.24 2.024, because 3 places moves means 10 power minus 3, so totally 10 power minus 9, it is nanocoulomb. Next, here in parallel circuit, V1 voltage V1 in parallel circuit, voltage V1 is Q1 by C1, which is equal, Q1 is 2 into 10 power minus 9 coulomb over C1 is 3 into 10 power minus 12 farad totally, which gives 667 volt, which is further equal 0.667 kilowatt. V2 similarly Q2 over C2, that is 2 over 10 power minus 9 over 6 into 10 power minus 12. Answer is 333 volt, which is equal 0.33 kilowatt. Then energy stored in series circuits. Energy stored in first, energy stored in C1, energy in C1 equal half Q1 V1, which is equal half into 2 into 10 power of minus 9 coulomb into 667 volt, which is equal 6.67 into 10 power minus 7 joules, which is equal 0.667 microjoule. Energy stored in second capacitance. Energy stored in C2 equal half Q1 Q2 V2 is equal half Q2 is 2 into 10 power minus 9 coulomb into 33 voltage, 333 volts, which is equal 3.33 into 10 power minus 7 joule, which is equal 0.33 microjoule. And for total stored energy in C1 and C2 combination equal 6.667 0.667 plus 3.3 into 10 power minus 7, which is equal 10 into 10 power minus 7 joule, then equal, which is equal 1 microjoule. Energy stored in combination is this. Next, this side. Now we got Q1 in parallel circuit. Q1 is C1 V1, then Q2 C2 V2, C2 V2, which is equal 2 into 10 power minus 12, 6 here, into 120 volts, which gives 0.72 nano coulomb. That is 3 times more here. That is Q1. Q2 is 3 times more than Q1 here. Then charge on the combination. Charge on combination, that means total charge. Which is equal C equivalent into V, which is equal 8. C equivalent is 8. C equivalent is 8 and 10 power minus 12, this is micro, and 120 volts, which is equal 0.96 nano coulomb. Both adding 0.24, 0.70 is 0.96 nano coulomb. Then total stored energy total energy stored. Half half Q half Q equivalent into voltage. Have what is Q equivalent? 0.96 into voltage is 120. Now 0.96 into 120 divided by 2 is 60. 57. 57.6. 0.96 is nanocoulomb, that is 10 power minus 9 and 120. So which is equal 0. Directly can find this one is nanojoules. 57.6 nanojoules. So far we discussed a lengthy problem on energy total capacitance in series and parallel, as well as energy stored in the circuit in both series and parallel, as well as we wrote how to find energy stored in capacitor. We have done. Please subscribe our YouTube channel.